instrument lab, and I'm doing some of the machine learning topics, such as compression sensing techniques for sensor data. So today, unlike an academic lecturer, actually I want to give a basic idea of the technology, the compression sensing technologies, and with my personal interpretation about the theories and some of the case studies. So after the talk, I will share with you the slides. So please, focus on my talk, and let's start. So in this talk, as I mentioned, first of all, I will talk about, what is the compression sensing, the background of these technologies. Then I will try not to focus much on the mathematical details, but I use my personal interpretation to explain the basic theories. So for the case studies, actually today I plan to focus on 3 cases. The first one is the medical imaging examples, which we can also consider as a sensor network problem. The second one is the wearable EEG, and actually it has linked to many applications in the area of the wearable devices. And as the compression sensing techniques, is relatively new technique and evolves very fast. So actually already has some applications in machine learning. So in the last example, I will talk about how people apply the compression sensing techniques to the recommendation systems. Okay, so let's start at the concept of compression sensing. So actually, what the compression sensing do is that, as we know, today we have seen more and more sensor network, and also as well as many variable sensors. They collect a huge amount of data. So, but however, due to some hardware capabilities, such as maybe for some sensors it has limited battery power, or for some sensors it has limited computational capabilities. So, actually, it requires to compress the data at its sensor end, and then send those compressed data to the cloud or to the computer, which have more computational capabilities. So what's happening? On the remote end of the computer, we want to make use of this data to extract some of the features and to make predictions and to make some decisions based on the information we have. But of course, in order to do the data analytics, we need to recover the data from its compressed version first. So in that sense, the compression sensing actually contains 2 parts. The first part is the data compression. So how we can compress the large amount of data to a small file size, a small version. And then when we want to make use of data, when we make analysis from the data, we try to recover the original signal. So this is 2 parts of the compressed sensing. So at this point, maybe you will ask me, why we need a different compression techniques? As we know that, in nowadays there are many data compression techniques. The most popular one is the JPEG wavelets, right? They are very popularly used in image processing as well as other areas. So the point I want to say today is that the compressed sensing techniques is extremely effective and useful for sparse data. In contrast, the traditional compression techniques, they are not efficient for sparse data. So, as here I give you an example on what is the sparse data, what is not. So, for example, for the matrix data shown on the left, there are only 1 or 2. Only a very few entries which is non-zero, which have the meaning that we want to make use of. Then for the rest of the entries, it's just 0 or doesn't exist. But however, on the right, on the figure for the figure on the right, this is the typical images, right? So actually, it is not. If you look at the grayscale or RGB scale, in a matrix level, you'll find that, I mean, this is actually a non-sparse data, where most of the entries have meaningful values. So the point is that why, I mean, the traditional compression techniques like JPEG is not effective for sparse data. So let's look at a very simple numerical example here. So for people who are not familiar with JPEG, so basically JPEG actually, they use a discrete cosine transform, which is a modified Fourier transform to convert the image. Here we look at the image, I mean, as a 2D matrix. So we convert this 2D matrix from the spatial domain to the frequency domain. Then we will find that, I mean, there are some insignificant coefficients in frequency domain. So in the compression stage, actually we just try to ignore or compress those insignificant coefficients. And at the recovery stage, we do an inverse Fourier transform to recover the images. But however, if we have a sparse data, so you can see the example where we have an array, is 10 entries, and only one entry have non-zero value, while the rest are all zeros. So if we do a Fourier transform, we will see that actually the sparse data has a comparable coefficients over all the frequency domain. So let's say if we do the data compression from the Fourier transform, let's just keep the first 5 coefficients in the frequency domain, and we do the inverse Fourier transform to recover signal. And you can see that actually this data has been distorted a lot. So from this simple numerical example, you can see that actually the JPEG, I mean, those compression techniques is not that actually effective for sparse data. So that is the motivation that we need to come up with a novel compression techniques for sparse data. As nowadays, I mean, the sparse data is a lot in many applications. So now let's focus on the first stage of the compressed sensing, the data compression part. Okay, so actually, if you think about the data compression, the essence of the data compression is that we try to compress a signal, maybe with a higher dimension into a small dimension. So in that case, I mean, the storage of the data is reduced, right? So in compressed sensing, it is achieved by building up an underdetermined linear system, as shown in this equation, y equals to cx. So here, the x is the original signal, which with n dimension, and y is the compressed version, which I mean with a shorter dimension. And here, the compression matrix C is predetermined, where the compression ratio actually is m over n. So later on, I will talk about more on, I mean, what kind of conditions we need to satisfy for such a C. So dimension, I mean, basically this data compression techniques is dimension reduction method. So then you may ask, I mean, what is the difference between this one and the other dimension reduction techniques such as PCA? So the advantage of these data compression techniques in compressed sensing is that it needs very few computational demands. So, and you will see later in the case studies, actually we can implement this data compression in hardware at all without any computational capabilities. But if we use PCA to do the compression, I mean, first of all, what you do is that you need to, I mean, normalize the mean and variance to minimize the computational errors. And then you need to find the eigenvalues and eigenvectors, I mean, for all the data you have collected. Then you pick up the the first n principal eigenvalues and eigenvectors to form the matrix C. So you can see that, I mean, in many of the examples, actually, we don't have this luxury to perform such a complex computational task. I mean, as some of the sensors may have limited computational powers, or, I mean, it needs to be compact, so it cannot have a, I mean, bulky space for a complicated hardware to perform these calculations. So as the data is compressed and sent to somewhere to be stored, so at a certain stage, we need to make use of the data, right? I mean, what sense if we deploy so many sensors to collect the information? I mean, of course, we need to extract some useful information for us from the sensor data. So let's focus on the second stage, is that how we recover the signal. This is very important, as if we cannot recover the signal in a very accurate way, I mean, the information will be distorted or even be lost. So actually, if we look at these problems in simple mathematics, actually what we are doing is that, can we fully recover the original signal X from its compressed version Y? So, but pay attention to is that C actually is the for this system actually is an underdetermined system, which means that there will be more variables to be determined compared to the number of equations you have. So the answer is, I mean, no, we cannot. I mean, you cannot always recover the original signal X, I mean, in general, from its compressed version. So here I just give you a very simple numeric example. For example, if we look at the compression case, y equals to x1 plus x2, which is we compress these two variables into one. So let's say now we are measuring that, okay, so the measurement output is 1. So what will be the pairs for x1 and x2? Then you will find that there are infinite many pairs of x1 and x2 that can give you the y equals to 1. So in general, I mean, this problem is not able to be solved. But however, this problem can be solved if there are some constraints, there are some assumptions that we can make for this underdetermined system. So in compressed sensing, as we know that the data we want to compress is sparse. So if we can have if we can make an assumption or know that the original signal X is sparse, which means that the maximum number of non-zero entry is S, which is known, and plus another condition that the compression matrix C satisfies some conditions, then in mathematics, actually, people can prove that we can recover the original signal X without any inaccuracy. So for people, I mean, want to know more about the mathematical details, actually you can look for this paper with, I mean, very rigorous mathematical derivations. But however, in practice, I mean, the sensor data we have is always corrupted with noises. So if we try to solve the problem by model this problem by looking for the minimum x is x L0 norm, then you will have the problem because the solution will be easily corrupted with noises. So people, I mean, come up with a more robust and more computational efficient approach, which is L1 norm minimization problem. And finally, actually, we can also use the least square minimization problems with L1 regularizations. So this actually this optimization problem, and I mean you can see that in many other machine learning problems. Okay, so here then I think a lot of people, some of people may ask, why we use L1 regularization? So can we use L2 regularization? So here I try to use an analogy to trying to explain the differences between the L1 and the L2 regularization with simple numerical examples. So for the figures on the right, first of all, we try to compress this original sparse signals. As you can see that this signal has 2,000 dimensions, but however only maybe 50 or 100 entries have non-zero values. Then we compress it and recover. So if we recover it by L1 norm minimization, actually, which is equivalent to the L1 regularization, you can see that even we add some noises to the measurement output, actually we can still recover the original signals. But however, if we use L2 regularizations, you can see that for those components with a huge amount of values or magnitudes, it will be penalized heavily. And for those zero entries, you have some small values for that. So actually, you can think of this comparison as the personal income tax rate. So for example, for L1 norm minimization, you can think of this regularization as, in certain countries, the tax rate is very low. So rich people, can still keep their money, right? So the tax rate is the same for everybody. But for the L2 norm minimization, sorry. So for people who earn more than 1 million, half of your salaries will be cut. Then this kind of income will distribute to those unfortunate people. So if you think about this analogy, it's quite easy to understand the differences between the L1 and L2 regularizations. As nowadays, every machine learning problems, one of the issues we think of is, can we use parallel computing for large-scale data sets? As these days the scale of data becomes extremely large, so people are trying to use parallel computing to shorten the computational time with more computational resources. Actually, in these slides, I will show that for the compressed sensing techniques, it's very easy to be parallelized. So if you look at the data compression, so here in the y equals to cx, this underdetermined system, we assume no correlations between events. So basically, for example, if you use a sensor to measure something or measure events, maybe at 1 second intervals. So during the data compression, actually we don't assume any correlations between the data you measure at the first second and the data you measure at the second second, and the third second, and the rest of all. So in that case, during your data recovery, actually you can use multi-thread computing to recover each event independently. So even if your the dimension of the data is so huge, so that your matrix C is so huge, there are already a lot of distributed methods available to solve this single L1 regularization problem. So as you can see that this compressed sensing technique is super real if your data is huge. Actually, it can make full advantage of the parallel computing to minimize the computational time for your applications.
So quick question. So you are parallelizing over time essentially. Is that correct?
So you mean
so
each of the data compression?
Meaning for your multi-threaded computing.
Okay.
So each thread will compute for each time. Is that correct?
Okay. So actually there are two scenarios. So the first scenario is that I mean you collect all the data, right? Then at some time you make a calculation. So in that case, maybe you can use CPU 1 to compute, to recover the signal x1,
sure,
which you collected at the time maybe t1, right? Then you can use CPU 2 to recover the signal which you collected at the time t2. So this is the first scenario. And the second scenario is that, I mean, in some cases, actually, at the time you are collecting the signals, then you can start to recover the signal which you collected maybe 1 day ago, 2 days ago.
Okay, I see.
Since,
okay.
I mean, these events are unrelated, uncorrelated.
Okay.
So is there any other questions so far? Okay, so next I will go through some of the applications, case studies, so that, I mean, you can get a better feeling, I mean, how these techniques is applied to the real applications. I mean, computer sensing techniques is, I mean, it's not a how can I say, it's not a universal technology. I mean, so that you can apply to every example, every application. It has its limitations. The limitation is the data sparsity. If your data is not sparse, I mean, these techniques is not that useful for your case. So so in the next 3 case studies, you will appreciate, I mean, the essence of the computer sensing. So in the first case study, so the computer sensing techniques has been already used in the medical imaging field. So here, it's position emission topography. Actually, it's a medical imaging instrument. It's a radiology instrument. And other radiology instruments are MRI, ultrasound, as well as others. So what the instrument does is that actually you will see that in this ring structure, it has many sensors deployed to capture the activities from the radio tracers. So before the imaging scan, actually you are injected with some radioactive tracers. So those tracers will stop at some of the molecules which have the problems, which may have the cancer cells. So during the scan, actually, the sensor can capture those information. I mean, where the tracers are stuck. So from the image, the doctor can make a judgment on where your organ has a problems. So during the scan, actually, what the sensor does is that it is continuously acquiring the signal at maybe 1 microsecond intervals. But however, people find that, I mean, at the same sampling time, not all the sensors will receive, I mean, meaningful signals. Only 1 or 2 sensors is capturing the meaningful signals from the tracers, while the rest of the sensors, actually, they're just measuring noise. They're just measuring, I mean, nonsense signals. So this is actually the characteristics of the data sparseness in spatial domain. So if you look at think about the sensor as a matrix, right? So at one time, there are only 1 or 2 entries are non-zero, while the rest of the entries are 0. So actually, people are thinking that whether we can use the compressed sensing techniques in these cases, such as to reduce the hardware complexities. Because, I mean, in hardware, you need to build up the electronic circuits to extract the signal measured from sensor, and then integrate all the information to do image reconstruction for the doctor. But however, if we build up like the picture shown below these pixel arrays, in a traditional way, we need to build up the readout circuits for every sensor. So it actually makes the hardware very, very complicated. So people think that is there any way that we, first of all, reduce the readout channels so that we can make the hardware more compact. And another motivation is that nowadays in medical imaging, people try to integrate several modules together to form a hybrid instrument. For example, now people are already integrated the PET and MRI together as a dual mode imaging instrument. So in this hybrid instrument, if you have a very complex hardware circuits for PET, actually the performance of the circuits will be significantly impacted by the strong magnetic field in the MRI. So this is another motivation that people try to reduce the readout channels. So compressed sensing actually is one way of doing that, and you can see that the compressed sensing actually the data compression part actually can be implemented in the PCB circuit boards. With only preamplifiers, resistors, and capacitors without any computational capabilities. So from these applications, actually, we can easily extend this to, wireless sensor network in more general sense. So from the figure on the left, this is the example we discussed just now, right? So we have a large array of sensors, only one or two sensors, and at each time give you the meaningful signal. However, for the rest of the array, actually it's just measuring nonsense noises. So for the figure on the right, actually you compare these two scenarios. So for the figure on the right, actually what people do is that people deploy a lot of sensors to monitor the pollution in some areas. So let's say if you can find some statistics showing that maybe at one time of the sensor measuring, there are only one or two, or only a few sensors actually they are receiving the meaningful signal, while the rest actually are receiving just noise or normal signal. So actually, you can apply the compressed sensing network because in many wireless sensor cases, for each sensor we want to because for many sensors it runs with the batteries, so the batteries have a lifetime, right? So we want to extend the lifetime of the batteries. So obviously, if you can reduce the data it sends out to the fusion center or to the computer end, you will definitely save your computational power or battery power for the sensor. Okay, so let's look at the second example, which is a wearable EEG. So EEG actually is not a very new techniques, because I think maybe several decades ago, right? People just doctors just place the electrode to your brains and try to measure your the signals from your brain and try to make some diagnostics about your brains from those brain activities. But nowadays, the trend is that people want to be fashion enough, and the technology engineers want to extend the applications to people rather than patients. So for example, we want to measure your brain activities at a very frequent time, so that it can build up the interface between the computer and the brains, so that if we can interpret your idea from these signals, so it's possible that we will link this with the computer. But however, I mean, for normal people rather than patients, certainly you don't want to have very bulky devices together with you, right? So actually, the people prefer that if we can have a very compact device, right, and you will not feel any burden if you wear this device. That will be perfect. But however, I mean, in order to make such a small devices, actually that put a lot of challenges on your hardware design, which means that your hardware must be simple as enough. Otherwise, the device will be buggy. But the problem of having a simple hardware is that the simple hardware cannot do many tasks as the computer can do, right? But however, for your brain activities, easily it can record up to several gigabytes. For the whole day. So the problem is that how you store such a large number of data. Right. This is a problem. Certainly, this data cannot be processed at the sensor end. We need to send the sensor, to some cloud or computer to process it later. So which means that actually we need to have a very good battery to keep sending the data. Right. People, of course, don't want to, say, change the batteries maybe within a very short time. So people maybe want to have such a device with a very long battery life. So this poses a lot of challenges on the hardware design. So, but however, if you see this, if you look carefully at these problems, you will find that actually the compressed sensing techniques is a very good candidate for these applications. So let's imagine if you can have data compression techniques that can compress the data without using, very complicated algorithms, then that would be great because compressing this data will be easily achieved maybe by a simple PCB board, right? Then after you compress data, you can send little data compared to the large set of data. So it saves your battery life, right? But however, at the computer end, when you receive the data, we hope that you can have a very robust and good learning algorithms try to recover data as more as possible. Because with this recovered data, you can do the post-processing, right? You can do the analysis of the brain activities. Try to correlate this disease to activities to certain diseases. And nowadays there's a trend that people is trying to build a large database with previous patients cases with brain signals plus the doctor's treatment conclusion. So they try to build up this huge database. So people hope that in the future, if your device can send your brain activity signal from your device, we can use some machine learning algorithms try to match the pattern of your signals to some previous signals already in the database and try to make a more accurate decision based on your signals.
In what sense is this EEG signal sparse? In other words, how do you...
Actually, that's a very good question. I will cover later on. So actually, why I pick up this example is that actually the characteristics of the data is different from the previous example. So you will see very soon. So to summarize, why the compressed sensing techniques is so attractive in EEG, as I just mentioned, because the EEG need long-term monitoring capabilities and large-scale data can be generated. Basically, it can be generated more than 1 gigabytes data per day, and that is for only several channels. So in other applications they deploy a lot of channels to monitor all your bodies. Definitely, in that cases, there will be more data generated. So the second thing is that the data needs to be processed with machine learning algorithms to make more accurate predictions. So And this is definitely, this will be done in the remote end with strong computational capabilities and large databases. And the variable, I mean, devices, because now people need a star, right? So we want to minimize the device as much as possible. Of course, as I mentioned previously, besides the battery power consumption, actually, there are other challenges, such as electrode technologies. I mean, how you design a material for the electrode so that you will not feel comfortable while the electrode is connecting to your brain. I mean, this problem is not within the scope of talk, as this is a material problem. So today's, actually, we are focusing on how to compress the data and recover the data. So as you mentioned, so you can see this is so the blue signals are the original measured signals from the EEG end, and the red one is the recovered signal from the remote end, the computer end. So as you can see that in this case, the signal is not sparse in time domain. So actually, for these cases, we cannot directly apply the compressed sensing techniques as what we did in previous examples. But however, people actually find that the data has sparse representations in terms of other basis functions. I mean, this is a little bit abstract to understand, but however, you can think of, for some time series signals, you only have maybe one or two frequency components. So in some applications, so in frequency domain, you will see that actually they are sparse in frequency domain. So, of course, in this EEG example, I mean, the details you can find from the paper. The basis functions is a little bit different from the, sorry.
If you're going to go to the trouble of dictionary learning, right?
The dictionary is fixed.
Oh, it's fixed.
Yeah.
Okay.
Because people do a lot of statistic studies on the previous signals measured, they find that they can propose a series of basis functions to decompose the signals.
Okay, so once you know a good basis, what additional benefit does compressed sensing offer? You've already, found an efficient basis, and you take a few terms, however many the top K terms. What does compressed sensing add how does it help?
So the question you have is that, I mean, since you already find some more suitable basis functions, right? Why not just represent in these basis functions and store in the device? So the point is that the compressed sensing can enhance the data compression. For example, let's say you have a basis function, right? You use maybe 10 basis functions to store the signals, right? In the compressed sensing techniques, we can further reduce to 5 or 4 maybe.
So this works when the new basis is good, but not so good that it's not sparse. So it still needs to be bad enough that there's some sparsity left over for you to squeeze.
Actually, the basis, you can interpret the basis as infinite number of functions, orthogonal functions, like what you did in Fourier transform, right?
Okay.
So if you transform the signal from time domain to frequency domain, right? So you have the basis function you use is a cosine t, cosine 2t, cosine 3t. Theoretically, I mean, this basis function is infinite because cosine t, cosine 2t, cosine 3t, I mean, plus cosine nt, right? They are infinite. So we assume that all the signals can be represented by a linear combination of these basis functions, right? So if we don't use compressed sensing techniques, the usual way we did is that we just store the coefficients for cosine 1t, cosine 2t, cosine 3t until cosine nt, right, to store these n coefficients and send it to the remote end, right? So in compressed sensing, I mean, there's no need to store, these n coefficients because we know that the data is sparse in these new basis functions. In other words, we know that maybe only one or two basis functions have some values, but for the rest, you have very, very small value. So in that case, I mean, instead of sending 10 coefficients for a signal measured in a time period, you can just send 2 coefficients or 3 coefficients.
I don't want to sound rude, but if that is the case, why would you send all of them in the first place? I mean, you can just send like a list. Like if only 2 of them are above a threshold. Let's say we threshold it, right? That's like a common thing to do. If only 2 terms are above the threshold, and just send those 2 terms instead of sending all n of them.
I see. So your question is that, I mean, since we already can find such basis, why not we just specifically point out that maybe the basis function number 2 have this 0.4 coefficient. We just store this coefficient and send it to the other end. So my answer is that if you use the thresholding, actually this demands more hardware modules to do this thresholding. So in compressed sensing, actually, if you remember my previous example, actually, to implement this data compression matrix C, actually, most of the components in the PCB I use is the passive components, resistors and capacitors. So actually, that will simplify your hardware a lot. I mean, compare, let's say if you want to use some thresholding circuits, then you need a lot of active electrical components to do that. So that will increase your battery power consumption.
Are you going to be talking about the design of the compression matrix a bit later, or should I ask now?
I will not talk more on the matrix, because the matrix, different applications may have, I mean, there are different restrictions.
That's the way I wanted to ask. Well, very briefly then, how broad a class of signals can a particular matrix handle? Like you want to use images. How given one matrix C, what kind of images can you compress?
Okay, so I treat this problem maybe into 2 scenarios. The first one is in the digital world. I mean, the original data is already digitized, right? Like you have an image, right? The original. So for this case, I mean, we can use some compressed matrix C and implement the data compression in software, right? Just in coding computing. So in that case, I mean, you can have a much higher data compression ratio. But however, if the original signal is an analog signal from the sensor end, for example,
case 1, okay.
For example, the PET, the medical imaging example. So actually, this is one of my research topics in my lab. So the data measured from the sensor actually has noises. It will corrupt with the signals. So how much compression ratio you can achieve actually depends on your signal to noise ratio, as well as the noises from the hardware circuits. Because if you want to have a larger compression ratio, which means that your circuits will be very, very complicated, then the noise level is higher. So in the real design, I mean, we need to consider this.
And does the
factors.
And does the degrade? Well, I don't know what's the word. Does the performance? How does it degrade with the SNR? Is it like a threshold? It's like, does it perform fine until a certain SNR and then it falls off a cliff, or does it gradually,
A very good question. So in this figure actually explains your questions. I know that maybe the text in the figure is not big enough, but actually what this figure shows is that. So for the figure on the top left corner, it has the highest compression ratio. It's I cannot see very clearly. I think it's around 50 or 60, the compression ratio. So what the author in this paper do is that they try to decrease compression ratio until the one shown on the bottom, on the right corner, the compression ratio is 2.5. So actually you can see that with bigger compression ratio, actually the signal is more distorted. Then the problem, then the question, maybe some of you may ask that. So what is the best compression ratio you need to choose? So actually, this question, depends on your data analytics. In the second step. So let's say that you have a very robust machine learning algorithms, right? You can still try to extract the information in a very good accuracy, even from very distorted signals. Then it doesn't matter, the compression ratio, you can use a very high compression ratio. But however, if you're, in some of the applications, right, maybe the data is too complicated, the pattern is too complicated, maybe the method you use is very robust to noise. Even there's a small distortion of the signals in the recovered data, your algorithm may got a problem. Then in that case, then you try to minimize your compression ratio. So actually it depends on cases.
And when you run this in hardware, is the compression matrix generated hard-coded, or is it generated, or how does that work?
So basically, in my medical imaging examples, how to say that? In some examples, they just use analog signals, try to compress analog signals to analog signals. Then your recovery is based on the analog signals. For some examples, after you compress data, you transform it to the digitized version and send it to the remote end. Sorry, did I understand your question?
No, I think I didn't explain it. The matrix C, the compression matrix.
Right.
When you want to run this in hardware, is this matrix C hard coded? Is it fixed, or do you generate it somehow?
It's fixed. It's fixed. It's predetermined.
Okay.
So sorry now.
I think I'm missing the whole thing here. So where is the learning part here? So if you're saying it's fixed metrics, C is not coding it.
You see the problem, the optimization problem actually is the same. In many other machine learning optimization problem, like a recommendation system, how you optimize your recommendation model, and how you optimize your coefficient recommendation model.
That becomes when you're analyzing it on the back end, not on the hardware.
Yeah, that is in the back end. Because in the back end, you actually the data you collect is very huge.
Your machine learning.
Sorry?
But the hardware that you're talking about.
So in the hardware, we try to minimize the computational calculation as small as possible.
That is already predetermined, right? That is nothing.
Yeah, this is the data compression.
Right.
The matrix is predetermined.
Right. So that is predefined. So nothing changing there.
Yes. So okay, so as your question asked, where's the learning algorithm? So in my last case study, actually, you will show. This is very recent results. On people trying to apply the compression techniques to recommendation system. I guess many of you is very familiar with recommendation system. So before I talk about that, how they apply the compression sensing techniques into the recommendation system. So let's try to think about how you build up the recommendation system. So can someone give a summary? Actually, in philosophy,
Well, you can take a matrix, an incomplete matrix, matrix with some filled values, and you can try to factorize it in terms of two lower rank, matrices as the product of two matrices, and you try to fill in all the holes in the product such that when you multiply them, you get as close as possible to the known values in the first matrix. So basically, it reduces to matrix completion and factorization.
Right. That's perfectly correct. So, and I want to add more on your point. So some other people, how they build out the recommendation system. We try to find out the correlations among some users on certain items. That is, if we want to make a prediction on what is the rating from user A on item B. So actually what we are, some of people were trying to find, is there any similar user right? Let's say user C, right? He made very similar predictions as user A on other items. So fortunately, the user C has made a rating on the item B, and that information actually we can make use of and try to guess what is the rating from user A on item B. So that is similarity methods. So actually, I mean, if we think of all the methods they use in the recommendation system, actually people are trying to do is that they are trying to find the correlations rather than those are random factors, right? So then we can say that if we follow this idea, we follow this objective, actually the things actually we are trying to do is that we try to predict a matrix which is a user item matrix N, which has a very small rank. So which means that a lot of users are dependent. They make similar predictions. Now also a lot of items, they also have their ratings on them also have correlations. Then to put a further step, can we hypothesize that the rank N will be the minimum if all the predictions is correct? So please pay attention to this. Is only the hypothesis. It may be wrong, it may be right, but this is the essence of how people apply the compressed sensing in the recommendation system. So to move a step further, so we formulate the problem in this way. So the question is that can we find a matrix X which fills up the unknown user item rating, which is required by some of the applications, and satisfy that because in the training examples we have already known entries for some of the user item rating, right? For these entries, the candidate matrix X, we must have these entries as identical to those unknown values in the training examples. So that the X has a minimum rank. So let's do a little bit complicated mathematics. Actually, you can show that the way we try to have a minimum rank X is actually is try to find a X with the smallest number of singular values. But however, this problem, if we want to try to solve this problem, is a NP-hard problem. Actually, basically, you don't have any efficient algorithms trying to solve that. Some of the basic algorithm you can try is that just a greedy search. You try all the matrices X, satisfy the conditions. Then you compare the X with each other and try to find a X with a minimum rank. So, however, as we know that in your normal recommendation system, right, you have very high dimension. Maybe you have 1 million users, right? Maybe 100,000 items. For such a real complicated problems, we need to find a computational efficient way to solve this problem. So then people, the details is in this paper, and people can prove that under certain conditions, actually, we can have an equivalent problem, which is we try to find the minimum sum of the singular value from this matrix X, and this problem is relatively easy to solve. And to move a step further, people can find a more robust and computational efficient approach, which is the equation shown on the left. Actually, if you compare this equation with the previous data recovery methods I talked about in the previous slides. Actually, you find that in mathematics is the same, right? Then another issue you may ask is that, okay, here, right, we only have the recovery problem. That is, we try to recover a matrix with unknown entries. Then what is the data compression part? So my personal interpretation is that actually the data compression part happens in nature. So what means that, in reacting, right, we have a very we have a matrix with all the entries already filled in, but it's just unfortunately we can only see its compressed version. So actually the data compression is already happening in nature, right? So now the problem is we try to recover the original matrix, and this method actually has been tested on the Netflix competition, the data sets. And you can find out more from the paper I cited here. So just a simple conclusion on the results. So actually it shows that the results has been improved in some sense, but it's just that the result is still not good enough compared to the Netflix prize winners. So why this happens like this? Okay, so this is my personal opinions on the challenges we face, how to improve further on these methods. So the first question is that just now, some of you may remember that actually we make a hypothesis here. Is that the problem we try to solve is trying to find a minimum rank X, right, with certain conditions. Of course, if you look at a lot of recommendation systems, you will find that actually the rank of this recommendation matrix is low. But is it necessary to be the minimum rank? Right, this is a big question mark. I don't know the answer. Maybe for some applications, yes, it might be the minimum rank, but for some applications, it may be not. Right, we need people to verify whether this hypothesis is true or not. Okay, so the other reasons why this method is still not good enough compared to the existing methods such as baseline, right, the metric factorization, right, plus modeling the time drift and other factors, is that actually from the model, the information actually we use is only the information on the user item recommendation matrix. We didn't make use of any other information. So the question is that how can we make use the other informations which may be available, right, such as sex, time drifting, geography, location in the model, right? What I mean is that how can we model it in a mathematical way? This is a very interesting topic. And for other challenges they face, that the second one is non-uniform sampling, which means that some users may have a lot of ratings compared to others. Actually, in the paper I cited in the previous slides, actually they find that actually this will affect the accuracy they make based on this method. So they try to make the modification on the method I mentioned, how to incorporate this scenario. So the solution they propose that they use weighted regularization. So it means that they use different weights for those users who make frequent ratings, and maybe less regularizations for those users who may make maybe one or two ratings. And the last but not least, the cold start problem. So what is the cold start problem? So the cold start problem is that in the training example, right, for some user A, right, we totally don't know at all, what this user does. The user may make no ratings at all. But I mean, in some applications, we need to predict what is his rating on some items, right? So this is the code style problem. So in this compressed sensing approach, so actually you will find that, I mean, if we have such users or items, actually the total row or total column is completely unknown, right? This will, I mean, automatically reduce your rank by 1. However, I mean, in the true reality, I mean, this user or item has some ratings, right? So actually, this cause some problems to the matrix properties.
When you change the regularization term, the second term, to have weights, does the theory of compressed sensing still apply? Because, well, that's it. Does the theory of compressed sensing still apply?
Yes, I mean, even in some sensor examples, they use weighted regularizations. It's just that, I mean, because since this talk, I mean, I just try to give a very basic idea of what is compressed sensing. So I try not to touch too much on, I mean, those complicated cases. I mean, definitely, you can look for these cases on the internet.
And does compressed sensing demand uniform sampling? Does it work with non-uniform sampling, or does it not related to that?
It depends on how good the performance you want to have. So definitely, I mean, use weighted regularization is a method to try to improve the accuracy of the method if you face the, I mean, non-uniform sampling problem. But I mean, to what kind of performance you expect, it depends on your requirement. It depends on the applications. Okay, so this, I think this is challenges we face, I mean, for this compressed sensing approach to the computation system. But however, I want to point out that actually this field is evolving very fast. Actually, the compressed sensing techniques is first innovated in 2004, and the approach used for recommendation system, I only see it in 2009 and 2010. So this field is evolving fast. It may be, I mean, in the future, it may have I mean, some modifications, I mean, on this approach to give a even better accuracy than the conventional methods. Or it may not. I mean, definitely, I mean, for research, right, this is you have the risk. Right? Maybe some new approach success, some new approach fails for certain applications. So let's pay attention to this approach. It may be a totally disruptive technology to the current methods in the recommendation system. It may not. Who knows? So now let's come to the end of the talk. And here I just want to recap what we discussed about. So here today actually I just share with you introduction of the compressed sensing techniques, which is a new data compression and recovery methods. So as you notice that actually the most frequent word we use is sparse. So if your data cannot be represented in some sparse sense, then the compressed sensing techniques may not be suitable technologies for you. Then the sparse, actually we talk about different case studies to show that actually some of the cases the signal can be sparse in spatial domain. I mean, this is easiest to understand, right? For some images, right, maybe 1 or 2 pixels have some values, the rest have 0, right? For the sensor network, maybe 1 or 2 sensors is receiving the real events at a certain sampling time, while the rest are just receiving nothing or noises, right? And we see some complicated examples where the data is not sparse in spatial domain, like EEG signal, or I mean, some applications include your heart beating signals, right? I mean, for this kind of signal, definitely is continuous time series signals. It cannot be represented in any sparse sense in time domain. However, you can represent it in other domain like frequency or other basis functions. So actually, I mean, there are hardware already available. I mean, they can transform this signal into other bases with very simple circuits. So I mean, for this kind of applications, actually, the compressed sensing is also very useful. It's just that you need to play more tricks. So you need to represent the signal in some other basis and do the compressed sensing. So basically, I mean, if you look at what is common among those applications and case studies, actually all these sensor applications, it requires a large-scale data transmission, limited battery power, computational capabilities, and requires the device as small as possible. And the last case studies I've talked about the applications to the recommendation systems. So now currently the conclusion is that it helps achieve some accuracy, but however it's not as good as those methods used as Netflix prize winners. But I mean, since this is new technologies, there are a lot of things can be improved. It might be, I mean, a disruptive technologies in this new applications areas. So just, I mean, I just want to point out, let's pay attention to, right? But I mean, it might be also that it might be fail for the recommendation system. Who knows? Okay, so as this talk is just a very general introduction about compressed sensing, actually you can find more on Stanford course website. And the second link, actually, I highly recommend to all of you. I mean, this is a very resourceful website. It contains, I mean, both the recent developments, basic introduction of the theories, as well as the applications. Actually, this is a very resourceful website. Actually, if you want to know more about these techniques, you can take a look at this website. And also, if you want to have more discussion on your special applications, yeah, you are welcome. I mean, you can have a short talk after the presentations. So thanks for your time and attention. This is the end of the talk. Thanks. So is there any further questions you have?
So are you always sending actual data in the sensor or sensor sending only data?
Sorry?
Sensor sending always actual data or the data?
So your question is that does the sensor is sending the actual data or
Data of T1, T2, like say, we send something in T1, time T1, and sending in time T2. So it is always sending actual data, can I send at time T2, can I send delta between T1 and T2?
I mean, these two approaches, I've seen these two approaches in different applications. Actually, it depends on your applications.
If I send delta, then it becomes sparse, right?
Sorry?
If I was sending with delta, it's sending the whole image. Well, then it could be pretty much sparse.
Sorry, you mean the data you sent at
Delta, I say, I have made it, depends on the minute T1.
Okay.
Another sample is T2. And T2, I'm not sending whole image at the depth of T2. I'm sending the difference between T1 and T2.
He's asking about temporal compression.
Okay. I mean, it depends on applications. So for some applications, like the medical imaging instrument, actually, the events we capture at different timing intervals are totally uncorrelated. So I mean, which means that on time Q1, right, maybe sensor 1 get an event. Maybe at time T2, maybe another sensor get another event. And there's totally no correlation between.
No. So sensor 1, suppose you send it time T1, and sensor 1 again sending data set time T20. So can it take difference of T1 and T20 when sensor 1 is sending data?
Yes.
Sensor 1 always sends delta.
Right.
Sensor sending always delta, they're not sending actual event.
But for some cases, I mean, the data is sparse in the spatial domain, right? So maybe for sensor 1, right? I mean, most of the time, just give zero value. Right? It's just at a certain time it gives maybe 1 or 2. Right? So if you say the differences between the signals from the same sensor at each interval, in that case, right, maybe the signal you send is 1110, 1111. I mean, actually, I feel that this is not a good approach because in the hardware implementation, right, if you send a signal 1 compared to send nothing, I mean, it requires more. It requires more hardware capability on that. Because sometimes you need to do thresholding, I mean, in some cases. Although some cases may not, but in some cases you need extra step to process the data you send.
So sorry, one more question for you said you will do analog compression. I mean, you'll do compress sensing in the analog signal, convert it. It will still be in the analog, and then you will do quantization and convert it digital. Now, what happens when you convert? So I mean, does that signal, is that in some sense stable? Meaning, now does your quantization error throw it off completely that you cannot recover it later on? Does that happen?
Okay, I think the example you mentioned.
Oh, okay. This is again.
Figure. Right. I mean, for some for analog signals, definitely you will have distortions. That's not possible to have really exact recovery of the original signal. So the question is that on your data analytics in the second step, I mean, whether your algorithms is robust to those distorted signals, whether you can still extract the features without inaccuracy based on the distorted recovery.
I guess more than that, meaning how much does it affect? Do we know any guarantee about it? I mean, is it
depends on your applications.
Oh, I see.
Also the complexity of the problem, right? Because for my problem, I have the 128 sensors, and the compression ratio is 8. But I mean, for some other wireless sensor network, it has a much larger compression ratio than I have. Then their problem is much more complicated than I have. Okay. So yeah.
So for example, does your compression ratio linearly dependent upon your quantization error, or is it?
Oh, that's a very good question. Actually, in most of the cases, they use the same compression ratios. But I've seen, applications and papers, they use adaptive compression ratios. But if you use adaptive compression ratios, it needs more computational capabilities on the hardware, right? You need to decide at which point you need a higher compression ratio, at which point you need a lower compression ratio. Right? So that's a trade-off you need to face.
Once you've compressed the signal, how did you recover it again?
Back-end they've got a machine learning system that does machine learning recovery.
So
you just recover it like any of your.
Well, like solving this.
Yeah, exactly.
Try to recover the signal from this underdetermined system. But as I say, to guarantee the accuracy of your recovery, you need to have some conditions to satisfy, which means that the original data must be sparse in time domain or in spatial domain. In some sparse sense. And another thing is that you need to carefully design your C.
So numerically, how would you do? Would you be able to use something like a convex solver for this?
Yeah. There are a lot of solvers for that. There are a lot of solvers for that.
Actually, can you convert this into a linear program itself?
Sorry?
Do you need a convex solver, or can you solve it as linear programming?
Actually, for me, I use solver.
Okay, good.
Okay, so that's all. Thanks for your attention.